Algebraic Structures, Lecture 14, Fields, Characteristic, and Extensions. Let us start by recalling the notion of a field. A field is a commutative ring in which each non-zero element is invertible. Classical examples of fields are the fields of rational, real, and complex numbers. Let us remark that we always assume that a commutative ring or a field has at least two elements, 0 and 1, and they are different. A very basic property of a field is that any field has only two ideals, the field itself and the zero ideal. One consequence of this is the following claim: if K and K prime are two fields, and phi a field homomorphism from K to K prime, then phi is injective. Indeed, in order to prove this, we only need to show that it is not possible that the kernel of phi is equal to K. However, this follows directly from the property that phi must send 1 to 1, and 1 is different from 0 in K prime. Now let us discuss some very important examples of other fields which we will use today and in the rest of the course. First example is as follows. Let P be a positive prime integer. Consider the following ring. We take the ring of integers and we factor out the ideal, which consists of all integers divisible by p. So z divided by pz. The outcome is a quotient ring, which we usually denote by z sub p, and we will also denote the same thing by f sub p, because this ring is in fact a field. Proof. So we need to show that each non-zero element in z sub p is invertible. So let K be such element. Then of course P does not divide K. And since P is a prime number, it means that the greatest common divisor of P and K is 1. But then there exist integers A and B such that A times K plus B times P is equal to 1. And this means exactly that the class of K times the class of A is equal to the class of 1 in Z sub P. And this shows that the class of A is the inverse to the class of K, so the class of K is invertible. And this proves that Z sub P is indeed a field, because any non-zero element is invertible. We remark that the field F sub P is prime in the sense that it does not have any non-trivial subfields. The only subfield is the field F sub P itself. Indeed, any subfield of F sub P must contain the class of 1, that's the identity element, and then it must contain the additive subgroup generated by this class. But that subgroup already coincides with the whole of F sub P. Next important example of a field is the field of rational functions. So let K be a field. Consider the ring K of x of all rational functions over K, and this ring will be a field. So a rational function is an equivalence class of expressions f of x divided by g of x, where both f and g are polynomials with coefficients in k, and g is a non-zero polynomial. The equivalence of such expressions is defined as follows. F divided by g is equivalent to u divided by v if and only if f times v is equal to u times g. Addition of such expressions is defined in the following way. F divided by g plus u divided by v is equal to fv plus ug divided by gv. This is the usual addition of fractions. And of course we are talking about the classes of equivalent expressions. And the multiplication is defined as follows. F divided by g times u divided by v is equal to fu divided by gv. So this defines on K of x the structure of a commutative ring, And this is a field because we have the following inverses. F divided by G, the inverse of this expression is G divided by F as soon as F is non-zero. And then this G divided by F makes sense. So this is the second important example of a field. Next, so we have already shown that F sub p is a prime field. It doesn't have any subfields except for itself. And the field Q of rational numbers also has this property. So let's prove that the only subfield of Q is Q. Proof. Let F be a subfield of Q. Then, of course, F contains 1, the multiplicative identity element, and so it also contains the additive subgroup generated by 1. That's a group of all integers. Then F contains 1 divided by n for any non-zero integer n, because it must contain inverses. A field should be closed under taking the inverses. So we have the inverses of all integers, all non-zero integers. And we can multiply those inverses with integers. So this means that F should contain any k divided by n, where k is an integer and n is a non-zero integer. Because F is a field, so it should be closed under multiplication. Therefore, F is equal to Q because it contains all rational numbers. And this completes our proof. Now we state the following very important proposition about prime subfields. Any field F contains a unique subfield that is minimal with respect to inclusions. And this subfield is isomorphic to either the field Q of all rational numbers or to F sub p for some positive prime p. Proof. The intersection K of all subfields of F is obviously a subfield, because the intersection of algebraic structures is the same kind of algebraic structure. So we take all subfields of F, we intersect them, it's a subfield, it contains 0 and contains 1, so it's a non-trivial subfield. And this proves the first claim. This subfield, of course, is contained in all other subfields by definition. Of course, it contains the identity element, and so we can take G to be the additive subgroup of F, which is generated by this identity element. There are two possibilities. It might turn out that G is finite. Let's say it has n elements. N is a positive integer. Note that n is greater than 1 because we assume that 1 is different from 0. So this G cannot have one element. Also, of course, G is contained in K, because 1 is contained in K, K is closed under addition. If we assume that our n is a times b for some positive integers a and b strictly between 1 and n, then a times b in F will be equal to 0. But this means that both a and b are 0 divisors, and so they cannot be invertible. And this contradicts our assumption that F is a field. This implies that n should be a prime number, let's call it p, and then G, the set of all elements 0, 1, 1 plus 1, and so on, up to p minus 1, this will be a subfield of F, which is clearly isomorphic to F sub p. And so K is isomorphic to F sub p in this case. The second possibility is that our G is infinite, and then we should take this group G and consider the set of all expressions A divided by B, where A and B are elements in G and B is non-zero. And it's easy to see that this is a subfield, and so it must coincide with K, and it's clearly isomorphic to the field Q of all rational numbers. And this completes the proof. Now we can define the notion of characteristic. Definition: we say that a field F has characteristic P, which is greater than 0, if its prime subfield is isomorphic to Fp. Otherwise, we say that F has characteristic 0. And the characteristic of the field F is usually denoted by char F. Remark: so in this way, the characteristic of any field is either 0 or a prime positive integer. And of course, if the characteristic of a field is finite, then it coincides with the order of 1 as an element of the additive group in this field. So for example, the characteristic of the field f sub p is equal to p. Another example, the characteristic of the field of rational numbers is 0, the characteristic of the field of real numbers is 0, and the characteristic of the field of all complex numbers is also 0. And also, it's easy to see that the characteristic of the field of rational functions over f is the same as the characteristic of f, because those x's, they don't affect the notion of characteristic. Now we can talk about the main notion which we will study in the remainder of the course, and that's the notion of a field extension. Definition: a field extension is a pair k embedded into f, where f is a field and k is a subfield of f. For example, we have the following obvious field extensions. Q is a subfield of Q, Q is a subfield of R, and R is a subfield of C. Also, any field f is a subfield of the field of the rational functions over f. Remark: if k inside f is a field extension, then these two fields have the same characteristic. The characteristic of the field in the field extension is the same. Remark 2. As field homomorphisms are injective, any field homomorphism phi from a field k to a field f gives rise to a field extension from the image of phi to f. And of course, image of phi is isomorphic to k because any homomorphism is injective. And the aim of this second part of the course is to develop a theory to understand field extensions. Now let us talk about algebraic and transcendental elements. Let k inside f be a field extension. Definition: an element A of f is called algebraic over k if there is a non-zero polynomial f of x with coefficients in k such that f of a is equal to 0. Definition: an element A in f is called transcendental over k if it is not algebraic. For example, any element A in k is algebraic over k as we can take as our polynomial f of x the polynomial x minus a. Example 2. The element square root of 2, it's a real number. It is algebraic over q because we can take as f of x the polynomial x squared minus 2. And the last example, the real numbers e and pi, so e is the base of natural logarithm, and pi, that's a usual number from geometry which relates the circumference of a circle with the diameter. So these two numbers are transcendental over q. And the proofs of these two facts are quite non-trivial. We are not going to prove this in this course because we will not going to use it. First, let us talk how transcendental extension works, how we can have an extension when we adjoin one transcendental element. So let k inside f be a field extension. Let A be an element in f that is transcendental over k. Proposition: there is a unique minimal with respect to inclusion subfield capital K of f, which contains both little k and a. Moreover, sending a rational function f of x divided by g of x to f of a divided by g of a gives an isomorphism between the ring of all rational functions over little k and the field capital K. Proof: the field capital K is of course the intersection of all subfields of f that contain both little k and the element a. Since our a is transcendental, the value of any rational functions f of x divided by g of x in a is well defined, because g of a is non-zero as soon as g is non-zero. Also, this value is constant on the whole equivalence class of rational functions. So f of a divided by g of a is of course equal to f of a times h of a divided by g of a times h of a, for any non-zero h of x, a polynomial with coefficients in k. And this applies that the above map is a homomorphism of fields. So we can send a rational function over little k to its value at the element A, and this will be an element in F, and this gives an homomorphism from the field K of X to F. So on the one hand, the image contains K because capital K is minimal. On the other hand, of course, capital K should contain all rational expressions of the form f of a divided by j of a, because it contains both little k and a. Now we can talk about algebraic extensions. Definition: a field extension K inside F is called algebraic, provided that every element of F is algebraic over K. So for example, the trivial extension of F inside F is algebraic. That's obvious. Example 2, the field extension of rational numbers inside real numbers is not algebraic, because we know that e and pi, these are real numbers and they're not algebraic over Q. So that's not an example of an algebraic extension. However, the third classical extension, real numbers inside complex numbers, that's an algebraic extension. Indeed, let's take any complex number, a plus bi. Then, this complex number is the root of the following polynomial with real coefficients: x minus a squared plus b squared. So if you plug in this complex number as x in this polynomial, we get 0. And this is a polynomial with real coefficients. This means that any complex number is algebraic over R. Next, let us talk about finite field extensions. Let K inside F be a field extension. Let us observe that the operations of addition and multiplication of elements in F define on F the structure of a vector space over K. So since we can add elements in F, it's a group with respect to addition, and we can multiply elements of F with elements in K due to multiplication, and we have distributivity. So a bigger field is always a vector space over a smaller field. Definition: the field extension of K inside F is called finite, provided that the dimension of the bigger field F over the smaller field K is finite. For example, the extension of F inside F is finite because the dimension of F over F is 1. Another example, the extension of real numbers inside complex numbers is finite because the dimension of complex numbers over real numbers is 2. So we have a natural basis given by 1 and the imaginary unit I. Third example, the extension of rational numbers inside real numbers, this is not finite. Indeed, so we know, for example, that pi is transcendental, therefore the field of rational functions with rational coefficients is a subfield of R when we send the element x to pi. So we consider all rational functions in pi, and that's a subfield of the field of all real numbers. And this is of course not finite dimensional over Q because it contains polynomials, and polynomials are not finite dimensional over Q because the powers of the indeterminate, they form a basis, and that's an infinite set. So what is the relation between finite field extensions and algebraic extensions? So the fact is that every finite field extension is algebraic. So let's prove that. Let K inside F be a finite field extension. Consider some element A in F and all its powers, 1, a squared, a cubed, and so on. So we have infinitely many elements. Of course, it is possible that there are different I and j such that a to the power I is equal to a to the power j. But then a is a root of the polynomial x to the power I minus x to the power j. That's a polynomial with coefficients in k, of course. And so this means that a is algebraic over k. Otherwise, we have infinitely many different elements in F, and F is finite dimensional over k. So these infinitely many elements must be linearly dependent. And when we write a linear dependence between them, so there are some positive integer k and numbers beta 0 and so on beta k in our field little k, such that the sum I from 0 to k beta I times a to the power I is equal to 0. But then this means that a is a root of the polynomial with coefficients in our field little k, which looks as follows: the sum I from 0 to k beta ix to the power I. This proves our theorem. A very interesting property of finite field extensions is the following transitivity property. If we have two field extensions, little k inside f and f inside capital K, and both are finite, then the extensions from little f to the capital F is also finite. Proof. Let A1 and so on ak be a basis of the capital K over f. Let B1 and so on Bm be a basis of f over the little k. Let us prove that the products Bi, Aj, where I is between 1 and k and j is between 1 and m, is a generating set of capital K over little k. Indeed, we can write any element C in capital K as a linear combination of the Aj's with coefficients in f. That's because Aj's is a basis of capital K over f. And now if we take any coefficient which we got from this first expression, each of these coefficients can be written as a linear combination of the Bi's with coefficients in little k. This is because Bi's form a basis of f over k. And now if we apply distributivity, we get an expression of C as a linear combination of these Bi, Aj with coefficients in k. And so we see that capital K has a finite generating set over the little k, so it's finite dimension. Now we can talk about the intermediate fields. Let K inside F be a field extension. Definition: a subfield capital K of F that contains little k is usually called an intermediate field or intermediate subfield. For example, the real numbers is an intermediate field for the extension of rational numbers inside complex numbers. Example 2, both k and f are obvious intermediate fields for the extension of k inside f. And the interesting thing about intermediate fields is that we can characterize algebraic elements using intermediate fields. So in fact, we have the following proposition. Let k inside f be a field extension. An element A in F is algebraic over K if and only if there is an intermediate field K which contains A and such that the extension of little k inside capital K is finite. In order to prove this, we need some preparation. And we start this preparation by discussing the notion of a minimal polynomial. Let k inside F be a field extension and A an algebraic element in F. So A in F is an element which is algebraic over K. Now we can consider the map phi from the ring of all polynomials over K to F, which sends the polynomial f of x to f of A. This is a ring homomorphism. It has a non-zero kernel as we assume that A is algebraic. So there is a polynomial which evaluates to 0 when we plug in A instead of x. So it has a non-zero kernel. This kernel is an ideal of our polynomial ring, and the polynomial ring in one variable is a principal ideal domain. So this ideal is principal, which means that there is a unique polynomial, let's call it ma of x, with leading coefficient 1, which generates the kernel of phi as an ideal. So this polynomial, ma of x, is called the minimal polynomial of A, and the reason why it's called minimal polynomial, because this polynomial is a polynomial of minimal possible degree that annihilates A. For example, the element I in C, so the imaginary unit I, has the minimal polynomial x squared plus 1 over the real numbers. However, note that over the complex numbers, it has a minimal polynomial x minus I. So the notion of a minimal polynomial depends on both components in the field extension. The main property of the minimal polynomial is that it's an irreducible element of the polynomial ring. So let K inside F be a field extension, and A an element in F which is algebraic over K. Lemma: the minimal polynomial of A is an irreducible element of the ring of all polynomials with coefficients in K. And since it's irreducible, it's also prime. Proof. Let's write our minimal polynomial ma as f of x times g of x for some polynomials f and g. Then f of a times g of a is 0 in f. But f is a field, so it's a domain. It follows that f of a is 0 or g of a is 0. But due to the minimality of our m of a, we get that either f or g must have the same degree as ma. But then the other one should be a constant polynomial, it should have degree 0. And constant polynomials are invertible. Non-zero constant polynomials are invertible. And this implies that ma of x is indeed an irreducible element, and for principal ideal domains, irreducible elements are the same as prime elements. This we know. Now we can prove our characterization of algebraic elements. An element is algebraic if and only if it belongs to an intermediate field, which is a finite extension of the smaller field. So if A belongs to some intermediate subfield that is finite over the smaller field, then A is algebraic because any finite extension is algebraic. Conversely, let A be algebraic over the smaller field. Consider the map phi from the polynomial ring k of x to f, which evaluates a polynomial f of x at A. The image of this phi is a subring of f, and this image is of course finite dimensional over k, because in fact it has a dimension which is a degree of m a of x, because the elements 1, x, x squared and so on, and then x to the power the degree of ma of x minus 1 form a basis in this image. So we have a finite dimensional subring of f. The kernel of phi is an ideal generated by an irreducible element, and over a principal ideal domain, all such ideals are maximal. So the quotient by that ideal is a field, and which means that the image of phi is a field. And now we have a subfield of f, which contains A, and which is finite over the smaller field k. And this completes our proof. So this has several consequences. First of all, a field extension of k inside f is algebraic if and only if each element A in f belongs to a finite intermediate subfield. So that's a direct consequence. And a little bit more trickier statement is the following corollary. If both field extensions of k inside f and f inside k are algebraic, then the field extension of little k inside capital K is algebraic as well. So algebraic extensions behave transitively. If we have two algebraic extensions and we can compose them, then the outcome will be also algebraic. Proof. Let A be an element in the bigger field capital K, and f of x be a polynomial with coefficients in f such that f of a is 0. Let b0, b1 and so on bk be all non-zero coefficients of this polynomial f of x. For I between 0 and k, let fi be the minimal subfield of f that contains our little k field, and all b0, b1 and so on bi. Each bi is algebraic over k, because it belongs to f, and the extension of k to f is algebraic. And so it's also algebraic over fi minus 1, because fi minus 1 contains little k. So any polynomial with coefficients in k is also a polynomial with coefficients in fi minus 1. And this means that the extension from fi minus 1 to fi is finite, but the difference between them is just adding one element. And this means that this extension will be finite. We just take the polynomial ring and factor out the ideal. We get a finite extension. And due to the transitivity of finite extensions, it means that the extension from the smallest field little k to fk is finite. At the same time, consider capital K prime. Let's define it as a minimal subfield of capital K, which contains both fk and a. Note that A is algebraic over fk. This means that the extension from fk to k prime is finite, because we just add one element. And hence the extension from little k to capital K prime is finite, due to the transitivity of finite extensions. But then any finite extension is algebraic, which means that A is algebraic over K. Let us finish with two notations. For a field extension of K inside F and any subset capital X inside F, we denote by K and then X's in these triangle brackets the minimal subfield of F, which contains both little k and x. And in the special case where X consists of elements A1 and so on and AK, we write K and then in triangle brackets A1 and so on AK. Some additional problems and questions at the end. Problem question 1. Prove that Fp and Q are the only prime fields. Problem question 2. In the proposition about prime subfields, prove with all details that the set of all A divided by B, where A and B are in G and B non-zero, is a subfield. Problem question 3. Fill in all missing details in the proof of the transcendental extension proposition. Problem question 4. Prove that the set of all products Bi times Aj is a basis of capital K over the little k. That's for the statement that finite extensions behave transitively. And problem question 5. Prove that for any positive integer n, the elements a to the power I, where I is between 0 and n minus 1, where a is the nth root of 2, that's a real number, are linearly independent over Q. Thank you very much and see you next time.